The second part of this lecture will be on image enhancement, and we will talk about noise suppression, deblurring, and contrast enhancement. So the three types of enhancement, as I said, are these, but let's look at what they do in terms of their effects on the images. Here we have an original image of a magnetic resonance image of a brain. By noise, I mean really additive structures on the image that disrupts how it's seen. Blurring, meaning the image is blurred, it lost information in the content in the high frequency component, so the edges look less visible, it's less sharp. And the last part is an image that's either overexposed or underexposed, simply has very bad contrast. When we talk about image enhancement, we talk about reducing these adverse effects so that we can actually get the original image back. Now, again, to understand these effects better, we need to learn a little bit about the Fourier transform and specifically the power spectrum. So, we'll delve a little bit about the Fourier transform now. Let's remind ourselves what the definition was. Fourier transform was basically representing an image in terms of a linear combination of orthonormal basis functions, which are, in the case of Fourier transform, are complex exponentials. I could get these coefficients or the scaling factors by using the Fourier transform simply by multiplying the image with the basis function and taking its integral over the image domain. Given an image, we saw that we could actually look at the magnitude of its Fourier transform, which is informative in terms of at its center, where u and v are both 0, it's high. When I go to the corners, I actually look at higher frequency components, so the intensity of the magnitude of the Fourier transform gets lower. There are some lines that are indicative of the lines in the image, and so on. And then I also had the phase component, which looked very not informative, but actually it was super important to be able to reconstruct the image and had subtle clues. Again, when we talk about the Fourier spectrum, we always say that at the center, we have the case where the frequencies are the lowest, and as we go right or up, the frequencies increase in the positive direction or increase in the negative direction, and so on. So center is low frequency components in the image, and surrounding is the higher frequency components. We also saw the convolution theorem. We saw that if I convolve an image in space with a kernel, that meant multiplication of the frequency response or the Fourier transform of the image with the Fourier transform of the kernel. Vice versa, if I multiply an image with a kernel in the space, it meant convolving the Fourier transforms in the frequency domain. Now, one important point that we need to understand is what's called the power spectra of the images, which is simply the square magnitude of the Fourier transform of an image. This basically tells me the amount of signal at each frequency pair. At the center, where the frequencies are low, I have high amount of signal, and towards the corners, where high frequencies happen, I have low amount of signals. Images are almost always composed mostly of homogeneous areas. That's why at the center, I have higher amount of signal. Most nearby object pixels have similar intensities that contributes to these homogeneous areas. So most of the signal realized in the low frequency areas that are seen at the central part here. High frequency components, they basically tells us the contribution of high frequency sinusoidals in the image, which corresponds to high frequency edge information in the image. If I were to look at the power spectra of pure noise, I see something very interesting. I see that it doesn't follow the same pattern. It doesn't have high signal values at the center and low on the corners. Instead, it has similar signal values, similar power, all across the Fourier spectrum. And that's quite interesting. It has similar components in high and low frequencies. That basically means that if I look at the power spectrum of a noisy image, I can be sure that actually what I see at the center, the high values, they must really correspond to the image, because noise doesn't have high components at its center. On the other hand, because noise has contributions in lower parts, contribution to the higher frequency components. That basically means that here, I don't know if these values are coming from the image itself or they're coming from the noise. Okay. So if I basically look at something interesting, let's look at the ratio of the power spectrum of the image versus noise. And the power spectra, basically the square of the magnitude of the Fourier transform, is defined for every frequency pair U and V. So in this image, I have high signal-to-noise ratio at the center because the power spectra of the image is much higher than the power spectra of the noise. In the high frequency areas, I have low signal-to-noise ratio because the power spectra of the image is low compared to the power spectra of the noise. So signal-to-noise ratio really corresponds to the ratio. The signal-to-noise ratio really quantifies the amount of signal versus amount of noise present in any given frequency pair. Now, one obvious way to actually get rid of noise by just looking at the power spectrum is to say, why don't I just simply remove all high-frequency components in the Fourier transform of the image and reconstruct back the image itself. That way, I can actually get rid of the major contribution of the noise and get rid of the low signal-to-noise ratio areas. The issue is, if we do this, and we did it right here, so we multiplied the Fourier transform of the image with a circle disk, kind of a box filter in 2D, and reconstructed the image. Notice that we got rid of all high-frequency components of the image. That's quite interesting. It actually is much blurry. And this is logical, because by cutting out these areas in the frequency domain, I cut out contribution of all high-frequency sinusoidals, so information on the edges got lost. Now, if I actually look at what I cut out, if I actually instead now cut out the central part of the Fourier transform and simply reconstruct with what's left, I see that, I have the contribution of noise. I can see the noise pattern remaining for sure. But importantly, I see the edges of the image that were missing in the previous case. Okay, so this gives us a much better understanding actually of really the frequency domain and its relation to noise, its relation to deep blurring, its relation to contribution of the noise in the high frequency components, and the relationship of noise with edges. Okay, now we go back from our detour and start talking about how actually these concepts help us build enhancement tools. The first question that we will look at is a noise suppression. So we take a noisy observation here and we want to remove the noise to get back the image. And we will really look at two different types of filtering techniques. Now, in general, there are very specific noise removal methods for specific types of noise that are related to certain applications. Here we will only discuss about the more general options that can be applied more generally on any natural image. The first part is the convolutional linear filters, or in essence low-pass filters or low-pass convolutional filters. And the second part will talk about nonlinear filters, specifically because we will want to preserve edges without blurring them, which will become clear in a second. And in that we'll talk about two main avenues. One of them is median filtering, and the other one is the anisotropic diffusion. So let's start our discussion with the first part, the convolutional linear filters. In other words, the low-pass filtering. So the principle is rather simple. We've seen that in the power spectrum of a noisy image, central parts contain information about the low frequency components of the image, and their SNR is quite high. So our goal is to remove the low signal-to-noise part of the spectrum, simply, for example, by multiplying the Fourier domain with a basic mask. So this approach, we've actually already seen the results, but let's put it here for completeness. So we basically multiply this Fourier spectrum with the mask here. We get rid of all the high frequency areas where the contribution of the noise is dominant. Now, such spectrum filters actually create one problem that we've seen, which was blurring, but they create another problem, which is the rippling. So we've already seen the effects, but deliberately I didn't discuss it. Why? Because if I multiply something in the frequency domain, it corresponds to convolution in the image domain. And the frequency domain box filter's Fourier transform is a sink. And we've seen that a sink has these negative and positive reversals happening in high frequency areas. So if I look at the result back again, I notice that first, of course, convolving the image with a sink means that I have to blur it because I only keep the low frequency components. But I also see something odd. I also see that here I have some rippling effects that were not present in the image. These ripples are caused because of the sink's ripples and convolution of the sink with the image. Okay, so although it's kind of an ideal scenario, like a very naive and obvious approach, it has certain problems. The second approach says, well, let's not multiply anything in the frequency domain, but instead, let's try to design convolutional filters in the image space. I mean, in the end, they will, again, correspond to multiplying the image's frequency, the Fourier transform, with a mask. But maybe by designing the filters in the image domain, we can actually control its effect better. So we create low-pass filters, and our aim is really to create filters that will not cause rippling. So model convolutional filters, such that we'll have the convolutional filter and we have this frequency mask that will have no ripples in the frequency domain nor in the image domain. One such filter we've already seen. We've seen the average filtering or the box filtering that we actually studied when we were talking about the sampling. And this is one of the most straightforward convolutional filters. So the filter itself in the discrete case looks something like this, for instance. If we talk about a 3x3 box filter or 3x3 average filtering, it's basically 3 pixels convolutional kernel, all with 1, and divided by 9, such that the sum is 1, so that it averages the intensities underneath. We can talk about a larger filter, 5x5. In that case, I will have a 5x5 convolutional filter, again, all with 1s, divided by 25, such that the sum is 1 again, so that I'm averaging. So the nice thing with these is, I mean, there are certain problems. We've already seen them. It actually has these ripples and so on and so forth. But there are some problems, there are some advantages of this as well. And one of them is the separability. So I see that actually I can represent this filter by simply convolution of 2 one-dimensional filters. First filter will be vertical, 1, 1, 1 divided by 3. And the other one is the same thing, horizontal divided by 3. So convolving these, I simply get this guy. And this is very nice, and it actually comes because basically convolving an image with this convolution kernel is exactly the same as convolving it first with this and then followed up with this because convolution was associative. So that's quite nice because convolving with such a one-dimensional filter is so much more computationally efficient than convolving with a 2D filter. So there are some advantages of this box filtering even. Okay, let's apply the box filtering to an example that we've seen before. We now have this image again with some wheels. If we add noise to it and if we apply box filtering, what we see that actually the noise is gone, or like the effect of the noise is reduced, as you can see now again. But I actually blur the image too, so the results are quite blurred. If I actually do it a bit more, I see that it's even blurred even further. Now, what was the modulation transfer function for the box filtering, average filtering? If we remind ourselves again, if we talk about a 3x3 separable filter, I basically talk about this multiplication of 2 sinusoidals, which actually looks something like this. It is low-pass filtering for sure, but I also see that it has some ripples in the frequency domain, so it will actually create some kind of phase reversals like we've seen before. And increasing the filter size doesn't really solve this problem because, again, I have a low-pass filter, but I will have ripples, and now the ripples will be even more frequent. So actually, it's not even low-pass filter because you see that some of the high frequencies pass, and some of them are disrupted, they're suppressed, and some of them are reversed. So it is a very basic thing that you can use, but it's not the ideal thing. Okay, so far, we've tried actually masking frequency domain with a window type filter, and it had some disturbing effects. It created really ripples in the image. We also tried basically using a box filter to convolve the image with, and we know that it was low pass, but it actually created ripples in the frequency domain at higher frequencies and led to phase reversals. So what we want is, we actually want a filter that has no ripples in either of the domains. So we don't have these phase reversals and information content change in the image in the frequency domain ripple with the frequency domain ripples, nor we want to see ripples in the image. So what we want is something that doesn't have both. And actually the solution is very simple, and it's called binomial filtering. The idea is we take a simple filter like this, two components in one dimension, one by one, and then we basically convolve that filter over and over again with itself. That way, we actually get filters, the binomial filters in various sizes in 1D. Now, if we actually convolve a horizontal and a vertical version of this filter, then we get the binomial filter in 2D. So, in a sense, by construction, binomial filter is also separable. So that's nice. Now, what did we want? We wanted no ripples in the space and a frequency domain. So in space, obviously, this filter doesn't have any ripples. I mean, these are all the values, and there's no changes of signs. Its frequency domain, the modulation transfer function, looks something like this. And it also doesn't have any ripples, and it's purely low-pass filtering. So that's actually quite nice. That really gives us the advantages of no ripples in both domains. Again, let's look at the image. Now, instead of using the box filter, we will use binomial filter. We have the image like this, and when we now apply binomial filtering, we see that the noise is gone. Again, the effects is lowered, but again, we actually see that there is some blurring effect going on that we cannot escape. One important, interesting fact about the binomial filter is that if I take a binomial filter and convolve itself again and again, infinitely many times, in the limit, I'm approaching actually a Gaussian filter. So basically, I'm really approaching this squared exponential function. So actually convolving an image with infinitely many Gaussian filters, infinitely many binomial filters, corresponds to convolving an image with a Gaussian filtering or Gaussian smoothing, which is actually quite well known in image processing image analysis. And here the Gaussian filter, actually what controls the amount of filtering is this B parameter here, the standard deviation. Now, if I take this image and use Gaussian filter to basically remove the noise, I basically see that I really can get rid of the noise. I don't have any ripples in the image, so that's quite nice, and this actually can be expected due to the binomial filter, but the issue is it's still blurred. I still have these blurry edges, so I kind of lose the high-frequency information that I needed. The funny thing is, in the original image, the high-frequency information is clearly visible, but I cannot seem to remove it yet remove noise and yet retain those informations. Actually, linear filters cannot really solve this problem. We need nonlinear filters. So some small notes on the implementation of things. So separable filters, as I said, can be implemented very efficiently. So binomial filter, Gaussian filter, isotropic Gaussian filter, they're actually quite nice. They're separable. They can be implemented very efficiently. Large filters, implementing them in the spatial domain is a bit problematic because computational times increase, but instead taking the Fourier transform, for example, with fast Fourier transform, and then multiplying in the frequency domain can give you a faster implementation. Filters that actually use integers for coefficients can increase the efficiency. First, doing manipulations over integers much easily, and furthermore, you can really create operations of powers of 2 using shift operations if you can devise such a filter. And the Gaussian filter, as I said, there's a component B, the standard deviation, and higher B leads to more smoothing and blurring, and lower B, lower standard deviation, means fewer or smaller amounts of blurring. So let me actually conclude this part, this section or this video part with one question, and I will leave it to you to discuss. So we talked about the fact that we said that the linear filters cannot actually solve the problem and retain edges. So can you actually explain it in terms of the power spectrum, power spectrum of an image based on the SNR discussions that we had? So can convolutional filters do a perfect job separating noise from the image? Can they separate edge information from noise in the high-frequency components? If so, why? If not, why? And with that, I will end this video as well.